Okay, let's go back to the theoretical performance. Okay, let me think how to go about this. Okay, let's say if we have Okay, let's just keep this simple. If you have, let's say, a time series data, or maybe you kind of run your model and you have a reference that you collect from your sensors. For example, if this is what you get from your sensors data, maybe YT, right? Because you collect it over time. And this is your measurements, is your reference. What's gonna happen when you run a forecasting or maybe a prediction? You get y hat equal to fx, right? But the thing is, y hat do not always need to hit exactly where y was, right? Sometimes it may be here, sometimes it may be here or here. So there are certain variations. And what if I said that this y measurements that I have here is actually not measurements, but it's a noiseless, it's a ground truth, it's a noiseless reference. What's gonna happen? Okay. So that means that pretty much whatever you get y hat here that may be hitting somewhere around your ground truth value will almost look like a random variable to your reference. Because let's say if you have a linear system y hat here where you have fx, right? And let's say this is x transpose beta, where you suppose that you already learned this beta from your training system already. What you have as your prediction will depend on your input, because this one is already learned is whatever shaped according to your training data. But when you use it as a reference, in the inference phase, the only thing that changed is your input. Just think about if you use this linear model with whatever new data that your system may never seen before. That means that your output prediction y here will depend on the stochastic behavior of your input x. So if x is a random variable, let's say if x is actually a random variable, this means that when it multiplies with beta here, it will give you a y hat that is also a random variable. So let's consider this case. So when you have y hat that is a random variable, in a very general way, this y hat should somewhat center around the noiseless reference of your system. But it may not necessarily be the case. It depends on how your assumption here fit your ground truth reference. Because your model may not fit your ground truth reference, sometimes we will evaluate this with bias. Bias, by definition, is the expectation of your output y hat here from your linear model, or maybe any model, negated by your reference. And in fact, I should use the notation that is y_0 to denote that it is like a noiseless reference. So that's the first thing. So bias will tell you how is your, let's say, predictions in general deviate from your noiseless reference, or maybe the noisy measurements if you change from y0 to just y. But this depends on what reference you're choosing. Is this okay? So this is like a first theoretical performance that people sometimes evaluate. And maybe before I move on, let's carefully look at how I denote each of these. Okay. Sometime, but I think most of the time, you will see me write everything in capital. Let's say in these slides, which is the first one. Well, actually, the bias that you learned previously will become this term. But please take a deep breath in and deep breath out. It is not that bad. Okay, what I was going to say that let's consider a very simple linear model where you have only just one beta and one x, right? Then you can write y as like a beta x. It's like the y hat is like a result of the scalar multiplication. That means that if your beta is equal to 1, x equal to 10, then y hat is equal to 10. Like a simple like this. Because we will consider something a little major than that. That is, as we mentioned before, if our x is any input in this world, x will likely become a random variable. So in this case, if you have this x times beta, and x is a random variable, then it's better to denote it as a random variable. So I use a capital, like a slim capital letter here to denote that right now I'm considering x as a scalar random variable versus this one is just a scalar constant. Okay, this one is scalar random variable. Therefore, once you multiply the scalar random variable with a fixed scalar, a constant scalar, then you get another scalar random variable, because this one is like a constant. Beta is constant, right? So, as you can see, actually, these entire slides are using this notation. You have an input x that is a scalar random variable. You get the output y hat that is a scalar random variable. Actually, with this, you can measure the mean square error in theory, which include 1, 2, 3 terms. We will go over each of them, please don't worry. But we already go through the bias. That's how we interpret them. So for the rest, we will cover it now. Okay, one more thing. When we evaluate this output prediction y hat here, we normally evaluate with respect to the measurement y, which is a scalar censored value. But previously I said that the bias could be either this as a like ground truth, noiseless, or it could be noisy. It depends on you. But then in this formulation, actually this first term bias is with respect to the noiseless case. but we will see why it can become this noiseless case. Okay, you want to take a break for a time being? Okay. Let's move on. Okay. In order to consider this mean square error, we will separate it into two cases. The first case is when you only consider the stochastic behavior of x and you assume that you are comparing the output of your system with the noiseless measurement, no noise. And your second case will be the opposite. That is, you are considering the measurement with noise, but x will be a constant. Okay. So firstly, when we only consider x as a stochastic random variable, we know that the output from x here or fx here, y hat here, will have some kind of randomness. And if we evaluate the mean square error of this output, you can write it with this formulation is the expectation of your y hat with respect to the measurement y. But the measurement y will be the noiseless one, so you can change from y to y0 here. And actually these two, they are the noiseless case, therefore they're not random variable. Actually in these slides, I should change them to a small y0, like that. It will be more accurate. Okay. Then we will further derive from this term, because after you have this term, you can further decompose it. What you will get is that you will get the bias y0 fx square plus variance of the fx. What you will get, but we will show it now. Okay, let's first look at this formula. We have that this one is actually a constant because it's a noiseless reference. I'm sorry for writing it as a capital. It's actually a typo. Okay, once you have this reference and you know that in your target you want to derive something like a bias and a variance, pretty much the variance suggests that you should have like the expectation of that y hat, of that y hat, this one. So maybe let's just add this term, or actually this term could be written as expectation of fx. Like we have to kind of add this term and subtract it out. So yes, we add in this term and subtract it out. Okay. And everything, the square is still kind of like, actually I wrote it wrong here. Okay. Sorry. Okay, maybe I used a different color. The square is like the entire thing, so that you can subtract this one in and out, no worries. But what happened after that is that actually when you have this two term, everything square, it's like a plus b squared, right? But if you go back to combine them, it's the same, because this minus and this plus will negate each other out. Okay. When you have a plus b, everything squared is actually equal to a squared plus ab 2ab plus b squared. Yeah. So actually from here you can derive it that way, but in my opinion, sometimes it's better to just put the expectation on the same side. So this one, even though the negate is here, I kind of take it out. And then we'll have the y0, that is the noiseless reference, minus this expectation. So it will change from, let's say, a plus b to a minus b now. Yep. Then we will now plug in each term into this a squared minus 2ab plus b squared. Then you will get the term that kind of look like this. Okay, I actually put audited note because I taught it before, but please bear with me. When you have all this term layout, actually, as we know, when you have bias, right? The bias formulation is this formulation that is equal to expectation of fx minus y0. And this one you have y0 minus expectation of fx. So actually inside here, inside this square, it is a bias. So you have the expectation of bias square. But bias is already like a constant because you take expectation on random variable, it becomes a constant. Constant minus your reference, that is a constant, then eventually everything becomes a constant. So this expectation is just a constant of bias square. Okay, next. Now you have this term. Again, we have bias in here. As we know, bias is a constant. Therefore, what you have left is that you can take the bias out, maybe 2 times bias with the expectation of your fx minus expectation of your fx. And now you can take the expectation inside. Then it will be 2 bias expectation of your first fx, minus expectation of fx. This is like an expectation of your y hat, which you also don't know what's the value that was. But the thing is, when this one is expectation of y hat, it's already a constant. And you take an expectation again, then again it becomes like an expectation of your y hat, like you are negating itself. That's why this term will eventually vanish because of this. Finally, you have this term left. So you have this term and this term left. This one reduced to just by a square, but this one will have its own meaning. As you can see here, this is a bias of your fx. It's like expectation of your y hat, right? And this is your y hat minus everything square, and then expectation. This is a variance of your y hat because you cannot go further with it. If there's a square here, you can't dive in. So on the other word, this is like a variance of your y hat. But sometimes I might write this as a var x, or here the reason for have this subscription x here means that usually we know the probability distribution of our data. And if we think about the fact that fx is like a beta x, something like this, pretty much it means that when we take expectation of y hat here, there are two ways. If we know distribution of y hat, we can compute the expectation with respect to y hat right away. But if we don't know, we have to compute expectation with respect to x. That's kind of the reason why I denoted at x, because y hat is just a function of x. Okay. So that's the reason why we have this variance term and the bias square, which is written here. Yeah. Actually, I forgot this last equation. That's why it's kind of number 6, but it's gone. And in this case, y is noiseless. Now we will consider the next case where x is a constant. If x is a constant, many things will be removed because it's a constant everywhere. But then you will get the noise from your measurement noise, and that will be the only thing, only stochastic variable here in your system. So it's in next slides. Oh, okay, by the way, actually this function is used a lot if your measurement is assumed to be noiseless. So if your measurement is assumed noiseless, you can just use this equation right away. Or it is actually this equation without this variance. Okay. Okay, let's look at what it's like if your measurement has noise, but your x is constant. To do that, we will first assign that, with that case, if we consider it that way, we will just change our notation from x to just this small constant x. So it's like just a scalar value. Then we say that we have this epsilon equal to fx minus the noiseless y, which is actually should also be like a constant y0 because it's a noiseless y. Okay, so at first, as I mentioned before, if our measurement has noise, there's no way for us to go about it but to compare the performance of our model with that noisy reference. Okay, so our reference will be y. But yes, if we say that, if we know what the noise is, then we can decompose this y into y0, that was our noiseless reference, plus the measurement noise. And you can see the first one, fx here, is just small x. This means that whatever in this fx, the result will be a constant. And actually, this one is a constant as well. I'm sorry. And yes, we can keep decomposing this term. And as we give some kind of definition that we have this small epsilon to be the difference between fx and y0, we can plug it in here. And because this noise measurement will be the only random variable in our system, the expectation that we have to take for computing the mean square error will be computed with respect to the noise distribution. And from this equation, we can decompose into this one, simple. And from this one, if we assume that the measurement noise has zero mean, it will become, I'm sorry for the notation, it's going to be really confusing, but it shouldn't be too confusing. Not sure if that helps. Can you see that? So actually, this is very important. Because this epsilon is pretty much a constant, actually I could just decompose it into epsilon square, like that. And we have this term, which is the expectation of our measurement noise, plus the variance of the measurement noise. And I should use a square bracket, I'm sorry. If we assume that our noise has zero mean, that is, let's say it could be like a Gaussian zero mean with the uniform variance, then this means that this term will be equal to the sigma square, and this term will equal to 0. So we will have epsilon, small epsilon plus sigma square, which belong to this term. Or on the other word, this is like equal to sigma square, this equal to 0. Okay, so this means, what this means is that if we are not considering the stochastic behavior of x, we will have some deviation of that output function from the ground truth value, which should be y0, the small one, plus the variance. And actually we know that this term, if on the other word, if there's no noise, it's just this term, right? But this term, if x is a stochastic behavior, if x is stochastic variable, then it becomes this formulation. Therefore, you can put two things together. And if we consider both the stochastic behavior and, where is that? And the noise in the measurements, then we will get something like this. That is, we have this part due to the noise measurements, and this part due to the stochastic behavior of x. And to derive that, I think this is going to be something very familiar for you right now. So at first, we have this prediction of fx negate with the measurements that is noisy. We know that measurements can be decomposed into two terms, that was the noiseless reference and the noise. Then you still have fx, because this time fx is a random variable. Now you may be changing the, kind of like change the decomposition a little bit, where you have this noise isolated. Epsilon here, like that. So you have a minus b square. Then you can decompose it into like a square minus 2ab plus b square into this term. And after that, you can decompose your expectation. And for your first term, this is similar to your first case, where you have stochastic behavior of x, and you are considering your you're considering your reference as being a noiseless reference. Meanwhile, the other term, it's like it will depend on the rest of the components. For example, this one will then start to be somewhat, okay, this is a bias. We know this is a bias. Is it? Yes, it is a bias now, because if you take expectation over here, it's the same thing. But this one is expectation of our noise. 0 mean, right? So it could be 0. And this one is a noise variance. So if we go back to our first slides, we will be able to decompose this one. We know that it's a bias with respect to the ground truth reference and the variance of fx. And then we have this term in addition because of the noise in our measurements. Then it becomes this sigma square. So this is like a mean square error theoretically, like how it came to this term. It's a very long one. But anyway, actually, what is good about this equation is the fact that it tells you some facts about the performance of your model. If you have measurement noise, as you can see, the measurement noise is independent of your model. What it means is that if you have measurement noise, very unlikely you can design a model to suppress it. You cannot suppress this noise. That's why usually we will refer to as irreducible term. And as we have this bias and variance left, you know that bias kind of refer to how far your predictions generally deviate from your ground truth. And you have this variance term that is the variance of your predictions with the expectation of that prediction itself. So how sensitive your model was. It's like if your model is very inconsistent, very likely you will have a high variance. That means your prediction result could just swing. And for this one, how far is it shift from your ground truth? Okay. And usually, and actually this came from experiment. I'll just show you a little bit. Usually, people found that if you have a model, let's say if you have a model that you want to capture the tendency of the blue dots here, right? And this blue dots is like you're testing already. Then you may try maybe using polynomial regression to capture the value of your sample. If you use polynomial degree 1, you probably end up with like a linear line here. And if you keep increasing the degree of polynomial, what you normally see is that as the order of polynomial becomes higher, your model will become something that is deviate from your blue sample. And the reason for it to deviate is because it tries to capture the characteristic of your training to the point that it's no longer fitting your testing sample. So that's become what we call overfitting. Usually, if you start to measure the mean square error, what you will get is that your mean square error for the polynomial with the lower order like that, it will have something called high bias. And the reason for it to have high bias is because, as you can see, this line can shift very badly from the overall points. However, if you have the polynomial of order, let's say 5, which is this orange line, you can see that this orange line can well capture every point. So of course, its bias should be low, and the variance should also be low, because it's consistent with this blue dot. But the green line, however, even though it can pass through most of the blue dots, it actually also triggers something like this deviation and that deviation. These kind of deviation usually result in high variance. So usually what we get is could be summarized just like this mean square plot. That is, if we vary the degree, that is like the x label here, where you have like, let's say this is degree 1. And okay, in this plot, I only evaluated up until degree 17, which is around here. But if I keep doing it until degree 30, what I see is that, okay, for my training mean square error, it keep reducing because my model will perform just like this green line. It will start to fit every point in my training, but it does not necessarily fit every point in my testing sample that was the blue dot here. So that's why the error just could go up very high. It could just deviate in whatever way possible to match with its training. But if I use something really simple, like this first order line, like a degree 1, it would just look like this around here, the mean square error around here, which is high, but it's high because it's too simple. So this means that if I would just increase my complexity, maybe the degree of my polynomial, to a certain point, you can see the dip of the error. That is when your model is the best. It's the best not just for your training, but also for your validation. So usually, if you evaluate at this point, you will get the mean square error that reflect the low bias and the low variance. So only around this point, low bias and low variance. For those points before, usually it's a high bias. And usually the points after this is high variance. So I'll put this way. Can
I go out now? I have some business. 5 p.m.
โอเคก็ไปดูวิดีโอได้นะก็ okay so he asked to leave but don't worry he can watch the video on YouTube he's safe yeah okay so yes but again if we say that our model we say that the model that is very complex tend to have high variance. The fact that the model become more complex will also enable another feature that we haven't yet touched on. That is, if your model is complex, it means that it can capture whatever in your training data. That means it's highly flexible. Flexible. So if your model is highly flexible, usually refer to the fact that it has higher polynomial degree. Yeah. But at the same time, it could also have high variance. So it's like you have to balance between what kind of errors you would get and what kind of complexity you're getting as well. So sometimes we can plot out as this graph where if you have high flexibility means that you have a lot of polynomials. It tends to have high variance if it's too high. And of course, complexity of that higher order will be high because you have to compute a lot of flops as well. Meanwhile, for the simple model that was those on the left-hand side here, they tend to have high bias. And yes, when the model is simple, it's like a linear model. You can interpret it easily, so it's in high interpretability. So that's the gist of this. Okay, what's your question again?
Me?
Yeah.
I'm talking about this graph, the next one. So the graph is bias versus complexity.
Mm-hmm. Yep. This one?
Yeah, this one.
Yep.
Bias versus.
This graph is actually the mean square error. It's like overall. It has both bias and variance in it. So actually this is like bias plus variance. It depends on what is dominating. For this side, usually the variance is dominating. For this side, usually the bias is dominating. Yeah. Okay. And what else? Okay, I think lastly, before we finish this, which is not yet finished, nearly there. Okay. It's like, at the moment, we are learning everything theoretical. Very theoretical. We have this mean square error, like this expectation of y hat minus y square. Y is a measurement. It could be noisy or noiseless, depending on your case. Yeah. But empirically, usually we compute the mean square with just this. Like the sum square divided by m, right? And the question is, how can we interpret if we compute MSE in empirical way versus the theoretical one, right? So the thing is, to ensure that these two are resonating one another, there are a few things we have to do. Firstly, we have to ensure that the number of samples M here is high. That is, when you evaluate your testing set, you still need to keep your number of testing sample as high as possible. And the reason being that when the number of testing sample is very high, the law of large number will then apply. That means that if your measurement is very high here, the difference between your empirical expectation, which is this E bar here, minus the expectation of that was the mean square error in theory, this one here, the difference between them will be bounded. And that is like the law of large number. And this law of large number signifying that the empirical error can then approximate the theoretical one. So that means you can compute empirically the mean square error this way, and it will also reflect your variance and bias in the theoretical way if the number of measurements are high enough. And then, yes, the way that you interpret it, even though you may not be able to calculate the bias directly sometimes, usually the one with the low number of parameters will have high bias if it's very low. And the one with the very high number of parameters usually have high variance. But the one that was the most optimal usually lies somewhere in between them, and it will have low bias and low variance. So it's like you have to vary that number. You have to vary your parameters for that number, yes. Okay. I guess my battery is nearly running out again. Okay, this one will go really briefly. So that is about mean square error. And this mean square error also suggests another thing from this graph, is that when you want to test, it's like how you would select your model. You should first do your training and then use another set of data to validate them, to select what is the correct model parameters, what is the number of parameters that is the best. And actually, in here I wrote it as a testing, but it should be validating MSE. That will be better, because you only want to select a model and you want to use your testing data sample to evaluate your final performance. That's a better practice. Yeah. So yes, this graph will somewhat summarize what I just said previously again. So we probably have something like the curve where you have high bias. Sometimes when you have high bias, people will call it underfitting. And when you have high variance, you call it overfitting. And actually, the complexity here are not just the number of parameters. Sometimes if you, let's say, train a machine learning, especially those deep learning, the complexity here could also refer to the number of epochs. If you train many epochs, I'm not sure how to call it, very likely your model will fit your training sample to the point that it's no longer fit your validation. That's overfitting as well. So this complexity line, there are many ways to interpret it and many ways that you can make use of it. It could be either number of the model parameters or number of epochs, or maybe the model complexity. Yeah. Okay, this is more like an example. We can move on. Okay. Nearly the end. So I guess from the previous quiz, we need to know. Okay, now you know what's RSS. Now you know what the evaluation score that can give you the value between 0 and 1. And yeah, all this stuff. Okay, the second one will be about model selection. So yes, I will go over this now. Do you want to take a break? Okay. Can I please have a break for like 5 minutes because my battery is running out again?